Hey 13 DPs, welcome back to the Topic 6 recap. So we are up to part B. This is collision theory. So you guys know this really well, but just to recap, for a reaction to take place, there must first of all be a collision, okay? Second of all, particles must collide at the correct orientation. And the third factor is that particles must collide with the correct activation energy. And just a wee bit of a recap, activation energy is the amount of energy needed to start a reaction, so to get over the hump of a reaction, and that hump means to break the bonds in those reactant particles. So that's what it means by activation energy. So we know that particles move randomly, and that's because of their kinetic energy. And because particles are moving randomly, not all particles will have the same kinetic energy. Okay, so we have to use an average, and we relate that average to the absolute temperature of the reaction. So temperature in Kelvin is going to be proportional to the average kinetic energy of that substance. So increasing the temperature of a substance will increase its kinetic energy. So the Maxwell-Boltzmann distribution curve, they love asking these in diploma. So it's kinetic energy on the x-axis, and on the y-axis is the number of particles with kinetic energy, and the area under the curve are the number of particles in the sample. Okay, so we can actually use this to represent a few factors, but before we move on, particle collisions and rate of reaction. Because we know particles must collide, okay, we have to talk about the fact that some of those collisions won't be successful, and the fact that some of those collisions will not collide with enough activation energy to cause the bonds in the reactants to break, and therefore some collisions are successful and some collisions are not successful. A successful collision is one where they've collided with enough energy to break the bonds in the particles. Okay, now for a reaction to be successful, there are two factors. So one of them is the energy of the collision. So that's what I've just been talking about, enough energy to break the forces in the reaction. And the other thing that leads to successful collisions is the number of them, so the more of them. Okay, so let's talk about energy of collisions, the activation energy. So I did a kind of crappy diagram a bit earlier on, but if we've got reactants to products here, this hump is the activation energy. Okay, and the activation energy is the energy required to break the bonds in the reactants. It's the endothermic aspect. Now, if we just look here, this graph here is an exothermic reaction, and I know that because the products have got less energy than the reactants. And this graph here is endo, and I know that because the products have got more energy than the reactants. The activation for an endothermic reaction is way bigger than that of an exothermic reaction, which means it takes a lot more energy to start an endothermic reaction than it does to start an exothermic reaction. Okay. And only particles that have a kinetic energy greater than the activation energy can have a successful collision. So there can be other collisions, they just won't be successful. So we can then use this Boltzmann curve, and we can actually add activation energy. So this blue, if this is activation energy here, this blue area are all the particles that have had enough activation energy to have a successful collision, and all this white area, which is massive, are the number of particles in the sample that haven't had enough energy for a successful collision. So you can actually see that proportionally, most of the time, most of the particles don't have enough activation energy. Okay, and this is me just comparing the amounts of activation energy again. Far more activation energy for an endo than an exo. That's why more exothermic reactions are more common. So geometry or orientation, it means the same thing. So that's talking about how the particles collide. So if you want particles to collide, they have to collide correctly to allow the particles to kind of gain correct contact. Okay, so these are representations of incorrect contact, okay, not going to lead to a collision. But this one here will lead to a successful collision. You do not need to know how the orientations are going to be. It's just explaining to you that sometimes certain collisions will not produce a successful collision, because the wrong reacting particles have effectively collided, whereas those some collisions, the correct particles will come in contact with each other. Okay, so here's a picture, and this one's actually a little bit easier to see here. So this is not an effective collision, and that's because only these two terminal atoms are colliding, and therefore it won't lead to an effective collision, and so they will not form products. Whereas though here you can see they're both able to make contact, and they can make two new products. So in summary, for a reaction to take place, there must be a collision, and the collision must have kinetic energy greater than the activation energy, and they must have the correct orientation or geometry. So how can we increase the rate of a reaction? Now, I spoke about these earlier. So, there are two ways to increase the rate of a reaction. More collisions, because if there are more collisions, then more of them will be successful, okay? And if we increase the energy of the collisions, that means more particles will have that activation energy. So therefore, those are the two factors that lead to a greater rate of reaction. So what are the four ways we can do this? We can do it through concentration, temperature, surface area, and catalyst. And I'll go through these. So if we increase the concentration of something, there are more reactant particles in the same volume. The same volume is critical, because if you change the volume, you're actually changing the concentration even further, and so you're not comparing apples with apples. So if we've got more particles, what happens is there's a greater frequency of collision. Frequency meaning there are more collisions in a given amount of time. Now, because we're talking about rate, every answer must link back to time. And so it's a lot quicker to use the word frequency than it is to say there are more collisions in a given amount of time, or there are more collisions per second. So it's quite a bit easier to use this word frequency, and I encourage you to use it. So there's a greater frequency of collisions, and therefore the rate of reaction will increase. Okay, so here lower concentration, here higher concentration. There are more reactant particles in the same volume, so there'll be a greater frequency of collisions and a greater rate of reaction. You can add an extra sentence in there that there'll be a greater frequency of collisions, therefore a greater frequency of successful collisions and a greater rate of reaction. But that second collision part, yes, it sounds beautiful because it's a perfect answer, but you don't really need it. So it's concentration. It's nice and easy. So you talk about how the number of particles have changed in the same volume, and then link that to a greater frequency or a decreased frequency of collisions. Okay, just a wee note that pressure is actually the same as concentration, because if you decrease the pressure, the only way to decrease the pressure is to, increase the pressure is to decrease the volume. So here the volume's gotten smaller with an increase of pressure, and if the volume's gotten smaller but you've got the same number of particles, and concentration is a measure of the number of particles in a given volume, effectively you've just increased the concentration. So therefore pressure changes are actually concentration changes. So that's just a bit of an FYI there. Okay, temperature. Temperature is the hardest one to explain because you've got 2 points you must do perfectly. If we increase the temperature of a reaction team, that means that the particles will have more kinetic energy. And if they have more kinetic energy, then they will be moving faster. And if particles move faster, then there's just going to be more frequent collisions. Think about speeding on the roads. If we all sped at 100 kilometers per hour, there'll be far more accidents or far more collisions. Okay, so they'll all have greater kinetic energy, move faster, and therefore there'll be greater frequent collisions or more frequent collisions. The second factor, and it ties back to this, is the fact that because the particles will have more kinetic energy, more of them will now have the required activation energy, so then more of the collisions will be successful. So not only are there more collisions and the frequency of collisions gone up, but more of the collisions will be successful because more of them have the required activation energy. So really important you get those 2 points down. Okay, so if we look here, this is actually showing a graph with an increase of temperature. So the activation energy hasn't changed, but what you can see here is that we've got this red line which is shifted, the hump is lower and to the right, and I'm going to talk about this. And what you can see is that this is at a higher temperature, okay? And at a higher temperature, there's now a greater proportion of particles that have a kinetic energy greater than the activation energy, and so have a successful collision. Now, it's really important you understand, they get you to do this all the time in diploma, why this graph's hump is lower than the blue hump. And the reason why is because the area under the curve is the number of particles. And so the number of particles are not changing. It's just that their kinetic energy has gone up. So we have to make the graph lower in order to have more particles here. And it has to go further across because they've got all of the particles have now got more kinetic energy. And so that's why. So you have to make sure that this curve goes to the right and that its hump is lower. It's normally worth 2 marks. Hopefully that makes sense. The next thing is surface area. So surface area is related to particle size. The smaller the particle, the greater the surface area. And it's really important that you say more particles are exposed to the other reactant because it's still the same number of particles. So if we're comparing this could be 2 grams of magnesium and this is 2 grams of magnesium. So still the same amount. It's just that more of this one is exposed to the other reactant, okay, and therefore there'll be a greater frequency of collisions. Okay, so this one here, more particles are being exposed to the other reactant by increasing the surface area, and therefore there'll be a greater frequency of collisions and a greater rate of reaction. So we increase the surface area by breaking something up into smaller pieces or grounding it into a powder. Because you can see here, here's a piece of magnesium. There's not much surface area for those reactant particles to collide with, but when you break it up, there's loads more spots that those reactant particles can touch. Just a wee note here, if you do stir during a reaction, then you will actually increase the rate of the reaction because you will be effectively making particles collide more. So it's just a wee note, and I put that in there for kids who are doing IAs on this. Okay, catalysts is the final part of this. So a catalyst doesn't actually change what a catalyst does. I'll start with that. What a catalyst does is it reduces the activation energy for a reaction. So we know activation energy is this hump, okay? You can see here, this is a catalyzed reaction. The hump is way smaller than an uncatalyzed reaction, which goes actually all the way to the bottom. So what does a catalyst do? A catalyst lowers the activation energy by providing an alternative pathway for the reaction to occur. In other words, could you please rote learn that sentence, because that's going to get you a full mark. And we've learnt a little bit about catalysts in higher level content so far. Catalysts are quite complicated in how they occur, and they're very specific how they occur for reactions. So this is a general what a catalyst does. All catalysts lower activation energies, but they all do it differently. So this second part of the definition, by providing an alternative pathway, is just a simple way of us describing all catalysts together. Okay, so with a catalyst, more collisions will have the correct activation energy, so the frequency of successful collisions goes up and the rate of reaction goes up. Hopefully that makes sense. Okay, you'll always get asked. They love doing Boltzmann curve stuff. So if you guys can understand this, perfect. So with this one here, the activation's been lowered. So now you've got more particles that are going to have a successful collision. Nice and easy. Okay, and so when we talk about this alternative pathway for a catalyst, one example that we can talk about is a catalyst provides a surface, and when we did our transition metal topic, transition metals act as a surface, and it just means reactant particles can come together a lot more easily and react because the catalyst has provided a surface. Okay, very lastly, last slide, and I've got about 40 seconds. This is a graph showing a catalyst, and this is quite interesting. The amount of catalyst will also have an impact on the rate of a reaction. Okay, it's important to note though really quickly, a catalyst does not get used up in a reaction. Okay, so you'll still have it present at the end. Okay, team. Yeah, that's about it. So hopefully this is you've all understood it all. Any questions, ask them on Teams. Thanks, teams. Team. Bye.